we'll get started with the afternoon session. So I'm Mike Neese from Keele University. We'll be chairing this session, and it's 1 hour, and later on we'll have the sessions on collaborative and group work, so just keep an eye on the timetable for this. And our first talk in this session is given by Andrey Korolkov from the University of Manchester, and he'll speak on plane wave decomposition for discrete diffraction problems. Over to you.
Thanks. First of all, I want to say my thanks to the organizers for having me here. It's a great honor. Now I'm gonna try to give a review for the results we got or in the last few years in collaboration with Andrey Korolkov, and some recent results I've obtained in Manchester. So, and also I wanna try to show how the ideology discussed by Andrey Korolkov yesterday, introduced by him, about a complex dispersion diagram could help us to find some exact solution for discrete diffraction problems. So I will consider 3 problems. The problem for Green's function over lattice. We discussed it yesterday several times, so I'm gonna be very fast here. Then a bit more complicated problem of diffraction by a half line, and then a much more, or surprisingly much more complicated, a problem of diffraction by a right angle. And as we seen yesterday, I will be studying a discrete Helmholtz equation. So this part is a discrete Laplace operator, and this a wave number. So, and since I promote the idea of the complex or dispersion diagram, let's start from dispersion equation, but also we've discussed it several times yesterday. So we have a plane wave ansatz. Here, Q1 and Q2 are variables of that transform, and the dispersion relation is just a quadratic equation. So we can solve it with respect of one of the variables, and we will obtain a simple function. So this function can be described by a Riemann surface with 2 cuts, which, as also Andrey Korolkov showed yesterday, can be considered topologically as a torus. And here I draw a unit cycle which is an integration path for that transform, and it's also a canonical dissection of a torus. And there is a third way to percept the dispersion equation. One way is a branch surface, another is a torus embedded in a 3D space, and the third way is as a parallelogram on a complex plane. We can use the following change of variables, which is just a first Abel integral, and psi here is one form analytic on the complex or dispersion surface. Or, as we know, it is a Abel differential of the first kind. So, and then what I'm trying to do, I'm trying to say that to solve such a problem, we should use the following concepts, which I call the Zauberfield integral. We have a plane wave, we have a transformant, and we have an Abel differential. And then I say to solve each of the problems, we need to find the transformant, solve some functional equation for the transformant. It's very simple for the point source problem, where we don't have anything. For the half-line problem, we need to build the transformant as a meromorphic function on a 2-sheeted cover, and for the right angle problem, we need to build a transformant as a 3-sheeted cover. So I will speak about this in details a bit later. So the simplest case, we have a Green's function, we apply Fourier transform or Z transform 2 times, and immediately using the residue theorem, we get a solution. So what I do next, I just look at this solution and find out that this solution has a structure of plane wave decomposition. This part is a differential, and this part is a plane wave. And the integration contour is a cycle. And I just rewrite this solution in this form, and what do I get from such an understanding? I get a unique representation of the field which I can use for any observation point. I just need to move the contour of integration. And I can show that I can slide these contours smoothly without any problems and without hitting the singularities on torus, the infinities on the torus. So it's the simplest part. Then I'm trying to apply this ideology to the problem of diffraction by a half line. So following the Sommerfeld ideas, I apply the method of reflection to this problem. It could be done more or less in the same way, and instead of the original problem, I have a problem with a plane wave propagated on a 2-sheeted branch surface. And immediately, then again, I'm looking for the solution in the same form, and now I can formulate a functional problem for the transformant. I say we need to find a function that first is meromorphic on a 2-sheeted covering of a torus, and then it can have only poles that correspond to incident or reflected waves. This function can be easily guessed since we know a solution of this problem. So I just guess this function, and this part is what is. This part is a meromorphic of function that covers torus 2 times. To make it a bit visual, we can look at the torus as a branch surface. So what I've did, I've built a function that is analytical on this branch surface. No, it's here, and that's more or less it. But now we left with another important step. It is we need to guess the Sommerfeld contour, and also I following the ideas, the general ideas described by Andrey Korolkov, that the Sommerfeld contour is just some contour in the vicinity of the infinity. So I can deform these contours as 4 cycles that are very, very close to the infinity points. And here we have an analogy with a continuous case. So a canonical dissection units with cycle is a contour which is analogous to this one, to the contour for the usual or continuous Green's function. And this standard Sommerfeld contours, they are also can be deformed to the infinity. And from this representation, we get a very general result that for the discrete problem, the wave field could be expressed as residues of some algebraic function, even a meromorphic function. And also, to be complete, we can apply asymptotic analysis to this integral and get or some analogy with continuous case. We will have a directivity of the scattered field, which will be defined by some saddle point contribution, and we will have a plane wave contribution which corresponds to some pole. So here we have a full analogy. And another problem is a problem of diffraction by a right angle. So again, I apply the method of reflection by Sommerfeld. I got 4 examples of the angle but I will get, if I attach them, it will be a three-sheeted surface. And as usually, I say that I need to search for the solution in terms of the Sommerfeld integral, and I need to construct the transformant. But it turns out that in this case, it's much more difficult to do. So one cannot just simply build the transformant. And here I need to build a function analytical on the surface, meromorphic on the surface. So again, I have a functional problem for the transformant. It should be a three-sheeted on a torus, and it also can have poles that corresponds only to the incident waves. And here, with the trickiest part of our work comes, we use the algebraic approach, but very basic algebraic ideas. We notice that functions meromorphic on this covering, they form an algebraic field, and we will try to build a basis for this field. Here I will give some examples. First of all, with the trivial one, the field of all rational function on a complex plane form a field. I call it Ko, and then I need to build a field K1 for a torus, then K2 for two-sheeted covering, and K3 for three-sheeted covering. And the second fact I use from algebra is that I can build K1 as an extension of Ko of order 2. It means that I will need to add two functions to this field, and I will get an extended field that will describe all this function in K1. And the same with K2 over K1 and K3 over K1. And here are some examples. So let us consider the dispersion with surface, and if I add this square root, I will get all possible functions with that meromorphic on a torus as linear combinations with some rational coefficients. So these rational functions are functions of the field Ko. And then if I want to consider a two-sheeted covering, I need to add one, and with this one, and also. But now I took as R1 and R2 with the elements of K1. So I can also can use this.
Andrey, may I interrupt?
Yeah.
Just to follow better. So on the most simple language, does it mean the classical fact of representation any elliptic function in terms of Wiener-Hopf function? You open all textbooks and you see this.
Wiener-Hopf. Please say again. Yeah, I think you are right, but the idea is that I don't want to use Wiener-Hopf function.
Huh?
I don't want to use Wiener-Hopf function because I want an algebraic representation.
No, I understand you want to study coverings.
Yeah.
But still maybe the uniformization of elliptic of torus would be. So elliptic function, the Riemann surfaces for genus 1, they have a great advantage with any other with higher genuses, because uniformizations in elliptic function is very efficient. Okay, so this is side remark.
Let's discuss it. Yeah, I will. Anyway, yeah, that's and the problem here is that I need to find two functions that are analytical on this six-sheeted covering, and it's not a simple task. It turns out it takes with some efforts to build. And also I want to add, since since Anastasia going to talk about embedding in the next talk, this is actually, I am going to look for the solution in the embedded form. What I mean that I have a couple of basis functions, and I separate the dependence from like an angle of observation and the dependence of the incident angle. So I will have the dependence on the incident angle only on this rational coefficients. And there is a trick how to build such a function that lives on this three-sheeted covering. So I took, the problem is I cannot put poles arbitrarily on a torus. I need to satisfy the Abel criterion. And to do it, I take a canonical dissection and partition it into 3 equal parts. And I'm introduce 2 functions. That one of them has a double pole in one point, another, and has simple zeros in another 2 points. And the second one has poles and zeros arranged a bit differently. And then I have a function that has triple zero and triple pole. And then I take a cubic root, and immediately I get a function that is analytical on a 3-sheet covering. So the idea, I need to build a function that has a triple root, but not as a cube of some function analytical on the torus, on the original or dispersion surface. And another thing that, and then I just build this function, and to do it, it's a technical part. I need to algebraize Abel criterion to find the coordinates of these 3 points. And this is how this function looks. Okay, and summing up the solution, what I do, I build an algebraic field of function meromorphic on a torus, find branch points on a torus, then I solve a polynomial equation, which is Abel criterion, algebraized version of Abel criterion, build 2 basis function, and got the solution. And by the construction, this solution is in embedded form. And also, in order for you to believe, I did it numerically. So, numerically, it works fine. Okay, and now I want to say several words how it is can be related to the Wiener-Hopf method. So I will use some technique to derive a Wiener-Hopf equation for half line and for the right angle. And to do it, I will use a Green's formula for the discrete grid. I can build a total analog for this formula of continuous case, and I can introduce some analog of a normal derivative, which I will discuss a bit later, and obtain a formula like this, where I only have a summation on a boundary domain, and this thing acts as a normal derivative, and U and W is some solution to the discrete Greenwald's equation. And then, doing the standard trick, I am applying this formula to the half plane. Also, I need to symmetrize the problem. So I now I just have the problem in the upper half plane. I have Neumann boundary condition here. Dirichlet boundary condition here, and this thing acts as an analog of a normal derivative. And applying Green's formula with a plane wave and a scattered field, I will get an equation that is very similar to the continuous fine. And here it's a trivial fact, of course. The factorization of the kernel will be given as elements of field K2. So at least it's coherent, it's consistent here. And then I can do the same trick with the problem of diffraction by right angle. But now I apply the reflection principle to only halfway, and I will get like almost branch surface, but the thing that I will not get any boundary condition on vertical axis, and then I can apply Green's formula 3 times and get a matrix Wiener-Hopf equation. And after some algebra, it can be reduced to form like this. And now it's actually very hard to factorize this equation. But what can I do? First, I can notice this submatrix of a Danieli class. And the second thing, I can prove a theorem that if I know two functions from field K3, I can build a factorization of this matrix. Otherwise, the factorization will be given in terms of elliptic functions. So, but here I will be able to build it in terms of algebraic functions. So it's actually the main gain of this work. So it's actually all that I wanted to say. Thank you for
Okay. So you've left us with quite a bit of time for questions. Yeah.
Very inspiring. But actually it shows the difference in cultures. So you said that otherwise it can be only factorized by the elliptic functions. For me it is great. It means the answer. So it is factorization in elliptic functions. It's a good answer. So,
I can say what's the problem.
Not every matrix can be factorized in elliptic functions.
Yeah, that's true. I agree. But the problem, I didn't do it for this, but if you have a continuous case, you will have an expression, a function that you need. It's like cosine some alpha C over K, where this thing is a spectral variable, and if alpha is like alpha probably is just like 1/3. Yeah, I suppose it's like 3. So it's definitely a like an algebraic of a function of psi.
Here. I don't understand. So what is this formula about? So what do you want to say?
I want to say that like here, if I consider a continuous problem for the wedge, I will get a solution in terms of cosine and sine functions.
Okay.
But I will have an expression that a cosine of arccosine of psi.
No, yeah.
In this case, I can write it like using trigonometric formulas as some algebraic function.
Very good. But here it is a discrete version. So
yeah.
this is a way. So in a sense, this your formula for continuous would be limiting case of your
I mean, yeah, that's
so all the very nice connections. And by the way, your functions MQ1 and MQ2 can be also written in Jacobi elliptic functions.
Of course, that's
you can do everything in a very explicit way using just elliptic functions.
True.
And what is the beta? Beta than
Okay,
elliptic functions
okay.
are only modular functions. So this is,
Okay.
Another
Sure.
Yeah.
So at some point you go to a Riemann surface and consider it like a magic recipe that you get rid of branch points. And you probably, since you write some kind of generalization of Malhuizen's integral, so you implicitly apply Cauchy theory, right? You use residues and so on, right? Theory on the Riemann surface.
At which moment?
But my
Yes.
question is that
Yes.
if you, there is no magic. Basically, if you go to Riemann surface, you get rid of branch points, but you have A and B cross sections, and then you have discontinuity on A and B cross sections. I've never seen in the theory that you include this stuff. When you apply, for instance, Cauchy theorem, and you might use, of course, in generalization Cauchy theorem, that you will have also integral of A and B cross sections where the function jump. I mean, your integrals on the Riemann surface, right?
Yeah.
But
Why
the
it
function
would
is
jump?
multi-valued still on the Riemann surface because you have A and B cross sections.
But they are not
Go
branching.
up, you have period.
Yes, but they are not branching.
It's what?
They are not branching there, so you won't have jumps. Like at which point I will have a jump? I have a differential analytic on the whole manifold. That's the idea.
But,
Well,
always when you
But
go
of
to
course,
Riemann
I
surface,
can, like, if I have a contour that,
when you live on a complex plane,
yeah,
you have branch points, whatever you do with calculus, you always have branch cuts.
yes.
When you go to Riemann surface, whatever you do in there, you do
Yeah, that's,
A, B cross sections,
okay,
you
that's-
cannot avoid them.
yeah, that's
And I
true.
don't see them anywhere here. So you just write these cycles, but they should be involved somehow. The classical theory should be involved, and I don't see it. How you avoid this? By
Actually,
linear relation, by Riemann, they should all be here.
okay, if you,
They're not.
at which,
Right, some kind of. I think there is maybe I missed something. But
what's the genus of this surface?
one,
Huh?
it's torus. It's a torus. It's a torus
So you
over
mean
a torus.
All the coverings are not.
They are toruses.
No. But let's say not ramified.
No, yeah. That's them, yes, they are not ramified.
They're not ramified.
Yeah, that's the idea. I'm
But
trying to
you-
build
but
a
you
cover.
hit this point there, what there seems to me as a.
The analytic as function on a torus, as functions on a torus. So I can see the simplest example. I still have time. Where is? Okay, for half line, I got like this function. This function I consider as a function of Q1 on this surface, and it has no branching.
Everything would be much easier to follow if you write everything in elliptic function.
I'm sorry, I'm deeply sorry for this, but I think the answer is that I don't have ramifications. Yeah, that's a simple case.
your pictures have these A-B cross sections, but you don't use them, right? So they should be somewhere.
Like,
Do you just do it for fun, or why do you decide where they are? Because any theory of Riemann surface, whatever you're doing with Riemann surface,
I can
cross sections.
answer. That's an
I
easy
don't see them anywhere. They
question
don't
to
involve-
answer. So this
So you just write Sommerfeld integral from complex plane. and
The
so
Sommerfeld
on,
integral
so
actually-
define and so on.
okay. The Sommerfeld integral can be deformed into with two cross section like this. One like this and one like this. So that's what I can say. I use them pretty much.
But when you write Sommerfeld integral, you implicitly use Cauchy theorem, right? The integral of a closed contour equals zero, the deformation principle, everything.
Yes.
on the Riemann surface, when you do it, you cannot avoid A and B cross sections if you try to generalize that theory,
Okay.
because then you will have jumps on A and B cross sections.
Okay, I think maybe that's a good point.
So
to
it's not
just
so easy.
end,
Okay, yeah.
and maybe have the discussion after.
Okay.
We have to move on to the next speaker, so can we
Yeah.
thank Andrey?